back to where we were. So, as I was saying about the Industrial Revolution, we created the Carnot engine, and this is what converted heat energy to mechanical energy using coal and oil. It really started off with coal, but we moved to oil later, which kind of is the same thing. It results in steam that comes from a combustion reaction, and that's what named the engine steam engine, is the resulting steam. And exploded the world economy. Exploded it. And the world has run off a majority of coal and oil ever since. In the background, I don't know if that's real or a painting, but there you go. I think that's a real photo of a coal plant. Oh, there you go. So coal is the goat, right? Like we live in the society we do. It's been built on coal, and it still runs on coal and oil. So we can't exactly hate it too much. Can't exactly hate it too much. It did a lot for us, but now we're realizing as time goes on, and as humans, always inventing something with problems, we now know, hey, this isn't all that good. It has bad sides to it as well, right? Exactly. Sounds like great news. What's the problem? Greenhouse gases, that's the problem. It's come up again and again, and it's recent scientific studies. This is a picture of a greenhouse. You're like, greenhouse gas. What the hell is that? Why is it such a weird name? So greenhouse gas is any gas within the atmosphere that causes the Earth to warm, and this warming is caused by trapping radiation within the atmosphere and preventing it from leaving out to space. So in other words, these greenhouse gases, they absorb radiation and they get re-emitted in the atmosphere. They're prevented from escaping out to space, so they linger in the atmosphere and they absorb radiation, and that absorbing of radiation is what leads to warming. So they absorb more than they reflect, and they kind of sit around. They don't go away for sometimes as many as hundreds of years or so. Greenhouse gases are often very long-lived, all except for water vapor. So water vapor is actually not as bad. But yeah, and the reason it's called the greenhouse effect is because it's similar to the way a greenhouse works by trapping radiation. Yeah, it's silly, but it works. Funny name. A little more on greenhouse gases. You couldn't figure it out. The reason coal and oil are a problem is because they themselves emit greenhouse gases, as I said, from a combustion reaction releases CO2 and carbon dioxide. Sorry, those are the same thing. CO2 and H2O, water vapor, and carbon dioxide. Carbon dioxide obviously is the same stuff we exhale. The same thing is for photosynthesis, so carbon dioxide isn't all bad. But they're still greenhouse gases, right? They warm their planet, right? That's bad. We don't want warming, right? Oh no, warming, it's so bad. But they're not actually all bad. Greenhouse gases are actually great. They would keep the planet warm at night. If it weren't for greenhouse gases, Earth would be much like Mars at night. Temperatures will drop to as much as 100 degrees below the morning temperature. So imagine, like, oh my god, it's 100 degrees today. It's so hot. And then before you go to bed, it's like 15 degrees. You're like, what the hell? I'm freezing. I need a blanket. That'd be every day. It'd be terrible. It'd be terrible. But that's how it is on Mars because of its thin, thin, thin atmosphere. And that's how it'd be on Earth too if we didn't have greenhouse gases. So now Earth is turning more like Venus, turning more into Venus because we have too much now. We have too much greenhouse gases. So Venus has an extremely thick atmosphere, whereas Mars has an extremely thin atmosphere. So we got two extremes, and right between us, we have Earth, which is the perfect Goldilocks balance of atmosphere. You have Mars, which has almost not nearly enough atmosphere. Then you have Venus, which has way too much atmosphere. So you kind of have the three bears. Sorry, not the three bears. The Goldilocks and the bears situation here. Right? Venus too hot. Venus too hot. Mars too cold. Earth just right. Just right amount of atmosphere. So the problem, as we just stated, too much of a good thing is not a good thing. And we're throwing extra greenhouse gases, which I call GHGs. I'll still say greenhouse gas because it's easier for me to say. But in the presentation, GHGs. that were not previously there. This is throwing the natural order off, the natural variability of Earth, the energy budget, not equilibrium. It's like, what the hell are you doing? You're throwing stuff in here that was not here. What is going on? Remember, these processes of adding CO2 and removing it occur on geological timescales, so it doesn't normally happen this quickly, adding these greenhouse gases, and it takes a long time for them to be removed, right, through geologic timescales. So once you put it there, it's kind of stuck there for a long time, hundreds if not thousands of years, and that's kind of an issue we have. Is we not only are we ruining the atmosphere for today, we're also ruining it for our future generations. So keep that in mind. Remember that. So here's the energy balances. I've been teasing about it for so long, but it's the balance of incoming and outgoing radiation within the Earth's atmosphere and surface. Now, the greenhouse gases absorb radiation and re-emit this radiation back into the atmosphere. So this is kind of like what I was saying about the greenhouse gases, right? That's what they do. But the re-emittance, where we said greenhouse effect, so this affects the energy budget of the Earth. Great. So some causes that lead to changes of the energy budget include changes in albedo, which is the same thing as reflectivity, changes in cloud coverage, greenhouse gas concentrations, and aerosol concentrations, which aerosol concentrations are what we saw from the volcanoes, specifically volcanoes, very much so on volcanoes, and humans too, from burning coal. Coal releases a lot of aerosols, and that's why we don't like coal. Aerosols kill people, a lot of people, especially really bad in India and China right now. Aerosols are bad. So they cool the earth, but they kill people because they give you lung cancer, so they're not good. No, they're not good, except for sea salt particles. Sea salt particles, A-okay. Any other aerosol? No. Let's see. So if the Earth's energy balance budget is in balance, we call this equilibrium, which it should be highlighted, but it's not. Currently, the Earth is not at a state of equilibrium because of these sudden changes in greenhouse gases that we've been adding to the system. Scientists, this is another reason for the discrepancy. The climate change is complicated, is that scientists are working hard to find out the radiation changes that may impact Earth and how fast or slow climate change may move. Much of this is still for debate, and there are uncertainties. We do know typical greenhouse gas concentrations from previous warming cold periods on Earth, but not within a great deal of certainty. So we don't actually know how much the Earth is going to warm. And I can't remember the term right now. We have a term for it that tells you, I think it's the sensitivity, climate sensitivity, of how much CO2 does it take to warm the Earth this much? How much of an energy change to the energy budget actually cause? How much warming does it cause? Including feedbacks, because you have to include feedbacks, because we don't know a lot about feedbacks either. This is the biggest discrepancy. How much warming? It's not, is there warming? It's how much. And that amount, how much? Is it dangerous amount? We don't know. And that's something scientists disagree on. That's really what the 3% are talking about is this change in the energy budget significant enough to cause substantial enough warming for concern? Now, most studies, because there obviously have been studies on this, right? Because we're in 2024, of course there's been studies on this, suggest that yes, there's not enough really done on it, because I think Sabine Hoffenfelder talks about the hot models that just a lot of global climate models that there's a lot of variation in the models, so still there's a lot of uncertainty, so we don't know for sure. And the big one is clouds. We'll talk about clouds later. We don't know a lot about clouds. Here's an example of the energy budget. It's in watts per meter squared because that's the units for radiation, and 1 watt is 1 joule per second, and a joule is the SI unit for energy. The output from the sun on Earth is about 1360 watts per meter squared, which you can actually do the math to get there, but I didn't do it. It's too much. It involves knowing the solar output of the sun and then the radius of the Earth. And, yeah, silly stuff, right? So to the right, sorry, I'll go to the left first. To the left, oh no, I lost my pointer. To the left, we have an example of a simple energy budget for an atmosphere, a 2-layer atmosphere, which Earth, I think, is really just one. I don't know, we'll say it's 2, right? It's like 1, I think it's like 1. But here you go, here's the sun. It transmits this much energy through the atmosphere, shortwave radiation, right? The sun emits shortwave radiation. Some gets caught in the upper atmosphere. Half goes back to space, the other half goes down to the second layer of the atmosphere. And then again, half and half. But remember that when you got to the sun, when you got here to the upper atmosphere, you had 238 leaving, but you still have 238 from the sun. So now you have 476 on both ends. You still have this 238 from the sun, and now you have 714 leaving. So you only had 238 coming in. From the sun, you only had 238, but because of this atmosphere that you've built up, right, that absorbs all this energy, aka greenhouse gases. This is what the greenhouse gas effect does. This is what greenhouse gases do. They do this. They're trapping all this energy into this atmosphere and releasing it, warming the surface. So instead of just getting 238 from the sun, you're now getting 714 because the atmosphere trapped all this radiation, all this energy, and kept you warm down here. So this is what we're talking about right here. This is what we're really talking about when we're saying that the Earth is warming us through greenhouse gases. This is what's doing this in the process right here of the sun warming the surface of the Earth. Right? This is how much it does. But the atmosphere absorbing all this radiation and re-emitting it back out, it actually increases the total radiation and warms you. So there you go. And we're increasing this part, of course, the thickness of this atmospheric layer with more greenhouse gases. So, add another layer of the atmosphere. That's kind of what we're doing, slowly, very, very slowly. And then this is a global energy flow. So here's a more complex version of the thing on the left. This is like everything. So you have buoyant thermals, evapotranspiration, latent heating, which is latent heating is just a fancy term for, condensation. That's all it is, right? Condensation. And then you have, right, because condensation warms, right? Yes, condensation. Formation of clouds and all that. Evapotranspiration is evaporation and transpiration. How cool is that? And then this is how much energy gets reflected by clouds. This is how much gets absorbed by the atmosphere, which is kind of what we're saying about the greenhouse gases, right here. And yeah, there's a lot to unpack here in this diagram, and I'm not going to get into all of it, but it's a very cool diagram, very complex. Also, don't forget about the albedo of the Earth. It reflects a lot of the sun's rays as well. That's important, albedo. We'll talk more about the albedo of the Earth when we talk about feedbacks, which is what we're talking about now. And hold on, I'll make sure I didn't skip anything. I don't think so. No. Feedbacks. Not everywhere Earth warms at the same rate. So, when we say global average temperature, that does not account for local variations. The general rule of thumb is not greater than the latitude, the faster the warming. The Arctic warms faster because of ice albedo feedback. Right? Huh? You're confused. Well, we've been talking about albedo, but really is it? And what the hell is a feedback? I'm sure you know what ice is, though, right? Of course you know what ice is, especially for Mexican. Sorry, I gotta cut that out. God damn it. Feedback. A feedback is the response to a system after warming has been present. There are two types of feedbacks, positive and negative. And a negative feedback, which should also be bolted, but it's not. A negative feedback means the feedback leads to cooling of the Earth, and a positive feedback is the feedback that leads to warming of the Earth. So negative feedback means you're warming, and then this feedback actually causes cooling, and then a warming event, a warmer Earth causes this feedback to occur, and this feedback leads to more warming. That's a positive feedback. Negative feedback means it actually leads to cooling instead of warming, which there aren't many negative feedbacks. There are a few. I think, yeah, there are a few, but none that I talk about. They're not as significant as the positive feedbacks. Substantially outweigh the negative feedbacks. The positive feedbacks substantially outweigh the negative. And then albedo is simply a measure of the reflectivity of any object, but we'll say Earth for now. Values range between 0 and 1, where 0 means the atmosphere is perfectly opaque, and 1 means the atmosphere is perfectly transparent. So, a perfectly black surface is perfectly opaque, which means its albedo is 0, which doesn't exist. There's no perfect black body. That's also what we call it. Black body, white body is when you're a perfect 1 albedo and 0 albedo, respectively. So 1 would mean that our atmosphere is perfectly transparent, otherwise perfectly white. It just goes right through, does not absorb any radiation. Which those don't really exist. The 0 and 1 doesn't exist, but the in-betweens do. The reflectivity varies a lot over Earth. So there are many different feedbacks, and some are still being researched, but the most important ones, there's 3 that I'm going to talk about. First is the ice albedo feedback, which we just brought up. It's the largest feedback, I believe. Right next to the water vapor feedback is also a really big one. So it goes like this. Increased greenhouse gases causes increase in temperature, which we saw from earlier. Increased temperatures causes melted ice. And I should mention melting land ice is sea ice, right? If you melt sea ice, it's like putting ice in a cup of water. Your water level is not going to increase. But if you add ice to your water after it's already been poured, then your level goes up, right? You have mass that wasn't there before. That's kind of what we're doing with land ice melting. When land ice melts, you're actually increasing the sea level. And what else? See? So sea level rises. And you have a decreased albedo because ice reflects a lot more sunlight because it's white. It's very high albedo, reflects a lot of sunlight. The ocean is very dark and opaque. It's like 0.2 or something like that, whereas ice is like 0.8, 0.9, so it absorbs much more radiation, which causes more warming. It's also the same thing if you have a black car or a black shirt. You're going to feel warmer than if you had a white car or a white shirt. That's kind of what's happening. We're kind of adding black to we're painting our car black is kind of what we're doing with the ice albedo feedback. And it's warming faster because of that, right? You're uncovering a more opaque surface, which causes more warming. And this more warming from the decreased albedo just amplifies the effect again. Because more warming causes more melted sea ice, which causes more sea level rise, and decreased albedo, which causes more warming. Yeah, it's a loop. It's a feedback, as we call it. Let's see. Okay, the one positive thing is the oceans warm much slower than the continents because they have a much higher heat capacity. I didn't write it down, but the heat capacity of the ocean is about 4,184. It's probably slightly higher even because of the salt in the water. That's about well over 4,000. Then for the land, it's less than 1,000. So it's like 4 or 5 times. It warms about 4 or 5 times faster than the land surface. So substantial. It's pretty substantial. I think it's 1,004 for the atmosphere. So it's over 4 times slower warming than the atmosphere. And before I get into the water vapor feedback, let's look at our pointer. This is Greenland ice changing over time. And as you see, it peaked. It's been decreasing a lot lately, right? 2022. We're at 2024 right now. Obviously, right? That's when I filmed this, October 1st. Jimmy Carter's birthday. Happy birthday, Jimmy Carter. But this is total mass change, what I was mentioning, when you add the ice to your cup. So mass change is decreasing. This is the amount of ice. So the amount of ice is falling. And so this is actual data. I kind of added this trend line after. But yeah, you can totally see the way like the ice has been just totally, it's fallen pretty substantially now. Like year over year, like let's look at the trend line. It's falling pretty quickly. And it's very dangerous. Greenland, we want our polar bears, right? I like polar bears. I don't know if you like polar bears, but we want to keep them on this planet, and we're not doing that with releasing greenhouse gases the way we do into the atmosphere. That's causing this isobeto feedback, which is causing this graph over here. It's causing this graph to exist. Also, the isobeto feedback is the largest reason why the Arctic is actually warming much faster than the rest of the Earth. It's warming about like 3 times faster. It's because of the isobeto feedback. So that's why I say it's pretty important. If you look at climate data, I don't have it pulled up, but I was looking at Alaska data, and it was warming so much faster than the Los Angeles data I was looking at. Much more rapid increases in temperature, which is good if you're Russia, right? You want more people to live there, more favorable conditions. We'll talk about permafrost later as well. Anyway, the second feedback is water vapor, which is similar. You get increased temperatures from greenhouse gases, right? Increased temperatures. So then you have more water from the isobeto feedback, right? Melting ice. And you also have warmer waters. This leads to greater precipitation. You see warmer water and more water, right? And yeah, the warmer waters also leads to more evaporation. So it's warmer, so you're getting more evaporation, and which causes there to be more water vapor in the atmosphere, and more water vapor often means more precipitation. So you're getting more precipitation, which is bad, right? Because climate change, we're predicting higher total precipitation amounts. But you're also going to get more warming because water vapor is a greenhouse gas. So that's bad too. So you're increasing water vapor and you're getting more precipitation. So you're warming and you're having more precipitation. And yeah, that's kind of it. More flooding, but also more drought because climate change. Alright, now here's permafrost. In the continental Arctic, there's some areas that contain what we call permafrost, and this is ground that remains frozen year-round, almost permanently. The depths of this permafrost vary from a few feet underground to several hundred feet. And permafrost contains a large amount of stored CO2 and methane. Mostly methane. It's mostly methane, which is even worse than CO2. I don't know if I mentioned it, which I'm disappointed I didn't. But methane is about 34 times more potent a greenhouse gas than CO2. So it's very bad. And nitrous oxide, I think it is, from before, that we saw, N2O, is 120 times, I think, worse of a greenhouse gas than CO2. Which I haven't even mentioned that worse than CO2 thing. But we use it a lot. We use CO2 as a baseline to compare its severity and intensity of greenhouse gases. Now, when this permafrost that we talk about melts, and it's not supposed to melt, right? It's like permanently frozen ground. But since the Earth's warming, especially the Arctic, more than ever, this permafrost is beginning to melt and releases more greenhouse gases. So, yeah. Hold on a second. I have to change this slide here. Forgot about that. we're not having that in there. But yeah, permafrost contains. Sorry, let me restart. In the continental Arctic, there are some areas that contain what we call permafrost, and this is ground that remains frozen year-round almost permanently. And the depths of this permafrost vary from a few feet underground to several hundred feet. And permafrost contains large amounts of stored CO2 and methane underground. And it's actually mostly methane, and methane is actually 34 times more potent of a greenhouse gas than CO2. And then, as we saw earlier, nitrous oxide is actually 120 times more potent of a greenhouse gas than CO2. And I didn't mention this more than CO2 thing, but it's kind of a baseline we use when comparing greenhouse gases. And it turns out methane is a pretty bad one. CO2 is actually a weaker one, but we emit so much of it that it's a big problem. I don't have the graph right now. I might add it in here of the greenhouse gases that are from worst to best, or the amount of, how bad they are, which I should include that. I think I will. Melting permafrost also causes land subsidence. Sorry, I skipped something. So this permafrost has been frozen year-round, right? Frozen underground. Should never be melting, but it is because of the iso-albedo feedback. And, right, it's in the Arctic, so it's warming faster than normal. So now it's finally melting after thousands, sometimes nearly a million years. This permafrost is melting. It's just been sitting there. Now this frozen ground, it actually contains, a lot of greenhouse gases, as we saw, methane, but it also has other gross things such as ancient bacteria and viruses. So this also is releasing a lot of bacteria and viruses that weren't there before. So this graph here. I lost my pointer again. Showing surface water change from permafrost. I'm not sure what's going on down here, but up here, like this is where most of the permafrost is. This is showing you where the most lakes have been formed from permafrost, aka from the melting permafrost. You can see most of it's in Russia. There's some in Alaska as well. But look at Russia. I mean, wow. Of course, most of it's in Russia, and Russia won't do anything about it. They choose not to do anything. This is probably the Himalayas or something, to be honest. But the point is, Russia is the biggest contributor here from permafrost, and they're obviously not going to do anything because it kind of helps their economy, Also, melting permafrost causes subsidence, as I said, and it can lead to greater biodiversity and lake coverage, which we were looking at here. Only good if you're Russia, really. Anyway, the feedback for permafrost looks like this. So again, increased temperatures from greenhouse gases. Right? Greenhouse gases warm the Earth. The permafrost then melts from the increased temperatures, right? In the Arctic, this releases more greenhouse gases, right? CH4, methane, and CO2. And this causes more warming. And also, these ancient bacteria and viruses, which, who knows what they'll do to us humans and any other species on Earth. Here we go. Here's water vapor and clouds. This is what I've been wanting to talk about. This is the most complicated feedback and still not very well understood. I recently asked my professor about clouds, on the impact of clouds on climate change, and he kind of just said, we don't really know. He said, science is getting better. Still no defined answer on the severity, but yeah. So scientists have found that there's an increase in cirrus clouds thanks to warming and larger scale height of the atmosphere. So the atmosphere is, like I said, larger scale height. It's thickening. Right? We're getting a thicker atmosphere. Right? That's kind of what happens from greenhouse gases. You look at Venus. That's what's happened on Venus. Very thick atmosphere. But you have more cirrus clouds now getting formed. These higher level clouds. They're very thin. And they actually lead to more warming and cooling because they absorb more than they reflect. Yeah, that's one thing they do. And they don't have as much backscatter radiation, the short wave. But in the infrared, right, because that's what temperatures are. Temperatures affected by infrared. They don't reflect as much sunlight as regular clouds, I say regular, but as much as the cumulus, like here, these guys, these nice puffy guys, reflect a lot more sunlight than cirrus clouds, which I don't have a picture of. I should because they're really important in climate change. They actually have a net warming effect. They cause more warming. They trap more radiation than they reflect. So they're actually bad for climate change. These nice puffy guys, though, very good for climate change. They reflect a lot of radiation and they keep the planet cool by as much as I think 10 to 20 degrees Celsius, and they're very important. If we didn't have clouds, Earth would be much, much hotter because of increased albedo substantially. Right? Clouds are white. So, yeah, the albedo, that's a big one, right? So you're also reflecting sunlight that wouldn't otherwise get reflected and just make it to the surface, usually. So these clouds are blocking radiation from reaching the surface, and they're also increasing the albedo of Earth. So they're good boys. They're good boys. They are increasing our albedo and reflecting more sunlight. They are keeping us safe. But some recent research shows that these boys are actually decreasing, and stratus, which are also really good coolers, are decreasing with climate change, and they found a tipping point around 1200 ppm, which we probably will never reach, but this is the tipping point that I was talking about, where if you reach a certain point, a tipping point, it's like I saw a guy say, it's when you lean back in your chair and you eventually reach a point where you fall over. That's what a tipping point is. You reach a point that just skyrockets the warming. You eventually reach a point where the warming will just continue. The feedbacks or the causes, the things that will lead to the warming, are going to be unstoppable. You reached a certain point where you've reached a certain point in the warming of the CO2 addition to where you're going to have this extra warming now from feedbacks that you weren't expecting. And that this cloud feedback, if the tipping point is reached, it could add an extra 8 degrees C of warming. 8 degrees C of warming. Yeah, that's a lot. Just from this tipping point, like instant, like human time scale warming. So clouds are very, very important. And this is another reason we have to not release so much CO2 and kind of stop what we're doing, According to the study in 2022, they found that we concluded that as the ocean warms, the low-level clouds over the ocean tend to dissipate. So these are the marine stratocumulus near California. You get these stratoform clouds that block radiation. Now, if you live in California, you might think, oh, I hate these clouds. Like, it's cold in the summer. Why is it cold in the summer? Why is it foggy every day in the summer? Well, that's because of these low-level clouds, and you should be thankful, because if it weren't for them, climate change would be much, much worse, and the Earth would be much, much warmer, and you'd have a lot of problems. Precisely about 8 degrees, 10 degrees C warmer, so not good. Be thankful for what you have. Anyway, the researchers anticipate the greater CO2 concentrations will lead to more absorbing and warming clouds, cirrus, and less stratus and cumulus clouds. These will lead to reflection, that's supposed to be reflection, not re-election, and global cooling. So this is one of the articles. I think this is the one I quoted right here. Very interesting read. I do agree. I think that there will be less of these clouds and more cirrus, which is bad. And who knows the frequency. Also, I didn't mention it here, but a lot of climate models are bad at looking at clouds and water vapor because it's a microscale process, and climate models are global models, right? They're global, very low spatial scales, so they can't see these small interactions going on in the clouds. So they are really poor at forecasting cloud coverage, and as we said, that can impact the amount of warming substantially, right? 8 degrees, 10 degrees, all these numbers could be significant in impacting future climate change, and this is big contributors to the HOT models I mentioned by Sabine Hassenfelder. This is an argument the hot models argument, essentially. That clouds are a bigger contributor than we realize, which I think they are, scarily enough. Now, how much is a few degrees C? So this is the thing I was looking for, I wanted to bring up. This is the effects, the effective radiative forcing. So radiative forcing is important. This is how it impacts the radiation, the energy budget. Now, as you can see, there's a lot of uncertainty, and the calculations in the energy budget are also uncertain. So, like 1 watt per meter squared or something is kind of hard to calculate down to the nitty gritty. So, yeah. So CO2 is the biggest because we've emitted so much of it, and then we have methane here, and then N2O. Those are the top 3. That's what NOAA put out. And then here's CFCs, HCFCs, is fluorocarbons. Those are the 4th largest, and then those are the largest greenhouse gases that we have. And then these are negative, so NOx, which is an aerosol. And then you have VOCs and carbon monoxide, which actually warm the atmosphere a bit. So these two kind of cancel each other out. Then you have sulfur dioxide, the largest aerosol. And we don't actually know exactly how much cooling it causes. Look at the variation, that's a lot. But this is what's emitted by volcanoes, as we saw earlier, right? So volcanoes cause a lot of cooling. Black carbon, right? Slight warming, right? Because they absorb a lot of energy because it's black, right? So it absorbs some, not too significant, but there is some warming caused by black carbon. Organic carbon, actually, on the other hand, reflects energy because it's an aerosol. And aerosols reflect. They block sunlight. And then ammonia doesn't really do much. Anyway, now I was just talking about the little diagram. Let's talk about the slide. So a few degrees C. Why do we care about a few degrees C? Well, it's a big deal because it's a change in the average temperature. Remember what I said about land? It moves much faster than water because of the heat capacity. Arctic moves faster than anywhere else because of albedo and melting permafrost, as we mentioned. This is the main killer, though, the main driver that I want to tell you. My climate change professor, same guy as atmospheric chemistry guy, he says it's like having a fever. An extra 2 degrees C is a big deal to the human body, and so would it be for Earth's system. So adding 2 degrees C is a pretty big deal. It's like you warming by 2 degrees C. Oh, that's not good. Earth's climate is a sensitive system. That's the main driver here. Earth's climate is a sensitive system. And we're messing with that sensitivity. We don't know what its sensitivity is, but we're poking it with a stick. Let's see. Weather extremes. So with climate change, saying the average temperature will increase pale comparison with the true impact will be warmer climate will have greater climate extremes. Instead of just a few degrees warmer, you may have long 10 degrees C warmer than average heat waves, followed by cooler than normal temperatures, which result in average only a few degrees above today's average. So basically saying that the average temperature may increase by a couple degrees, but in reality you'll have a long heat wave followed by cooler than average temperatures, which will average out to be slightly above average temperatures. So that's kind of what we're expecting to see from climate change. You're also going to have exactly. It's less about warmer averages and more about greater extremes. So climate change is all about weather extremes. That is what climate change is about. So it will lead to further drought in areas that already see little rain. Areas that see a lot of precipitation will see extreme amounts of precipitation and more flooding. Hot areas will have hotter weather, more frequent heat waves. Extreme heat and drought has already been hurting the west coast of the United States and its economy. And I've said extreme heat. I haven't even mentioned Helene. Right? Helene's caused so many problems. Flooding is also horrible for the East Coast. So you have extreme drought in the West Coast, and you have flooding in the East Coast. So, you have polar opposites on both sides that are causing economic catastrophes. And then here we have kind of what the Hoover Dam looked like in 1983 compared to 2021, which was the height of a serious drought. And you see kind of the impact there, pretty substantial. All right, we're going to actually stop for today because this is getting too long.